Hello, let's get started with this afternoon session. But before we get started, I was told that Ahmed made an announcement about Steve Shanker's public talk tomorrow evening. He asked you to register. Apparently the link was not working at the time, but the link has been corrected, and so you are now encouraged to go register for Steve's talk. This afternoon we've got two talks, and we're going to start with Javier Magan, and so take it away.
Hi. Thank you, Rob. Hello, everybody. So I want to start by thanking Ahmed and all the organizers for the opportunity to speak here. Today I'm going to describe a couple of works. These works touch on different topics related of interest to the string community, such as modular invariance, the notion of completeness in quantum field theory, generalized symmetries, which we have heard a lot this morning, and two-dimensional conformal field theories. So these works were done in collaboration with Valentin Benedetti, Orazio Cassini, Yasusuke Kawahigashi, and Roberto Longo. So I want to start by explaining the motivating question. So the topic we are most interested in these days concerns the physics of what we call non-local operators. So what do we mean by non-local operator? So consider this ring-like region here, the region R. We say an operator is non-local in R if it is localized in R, in the sense that it commutes with local operators outside the region, in the complementary region R prime, but at the same time, it cannot be generated by local operators in R. So a paradigmatic example is a Wilson loop in pure case theories. So a Wilson loop wrapping this ring commutes with local operators outside, but it cannot be generated by local operations inside the ring because the gauge potential is not a good operator. So it cannot be generated by local gauge invariant operators along the ring. An operator that would be delocalized in the ring, but that would not be non-local from this perspective, would be just like a loop operator in which we exchange the gauge potential by a gauge invariant conserved current. That would be still delocalized over the ring, but it would be local with respect to this definition. Okay, so if this type of operators exist in your theory, the first remarkable consequence is that there is not the algebra that you assign to region R is ambiguous. There are two canonical algebras you can associate to this region. The first is the additive algebra. So this is the algebra of all operators that are localized in R, but that at the same time can be generated by local operations in R. This is the algebra that you could say the natural algebra that a laboratory localized in the ring would measure. We simply call it A of R. The second one is the first one plus all the non-local operators with respect to this definition. We call it the maximal algebra because it is the maximal algebra that is compatible with causality. And indeed, it can be nicely defined by this relation. It is the commutant of the additive algebra in the complementary region. Now, there are many interesting aspects of this notion of non-local operator, but one that is important for this talk is that it suggests an intrinsic definition of the notion of completeness in quantum field theory. This notion is very simple. We just say that the maximal algebra equals the additive algebra for all the regions. Equivalently, we can say that there are no non-local operators in the quantum field theory. So for example, as I said, a pure gauge theory has Wilson loops wrapping around this ring, so it has non-local operators, it wouldn't be complete. And in fact, one can check that this notion of completeness in appropriate weakly coupled scenarios coincides with the standard notion of completeness based on having a maximal lattice of electric and magnetic charges in gauge theories. But it is, of course, an intrinsic definition. It doesn't require that we think in gauge theories. And is the definition that we are going to use in this talk. So we are quite interested in these non-local operators, in this notion, but one important feature that is overlooked typically is that this notion of non-local operator is a relative one. So you can be non-local with respect to a certain region, but still you can be local with respect to another region. In fact, all non-local operators in relativistic quantum field theory can be locally generated in a ball that contains them. This is the original version of hard duality. By the way, sorry. So another way of saying this, the statement of completeness that maybe you have heard about in the past is that hard duality, we say hard duality holds in any region. So when these two algebras are the same, we say hard duality holds in the region. So the original version of hard duality, it was exactly that it is valid for regions that are balls. And this is, we could call it the fundamental notion, the fundamental hard duality, because it can be proven using first principles. For example, in conformal field theory, it can be in balls, it can be proven through the Bisoniano-Whitman theorem. At the more practical level, in this article with Horacio, Marina, and Diego, we show that Wilson and Toff-Loop, by explicit construction in both abelian and non-abelian theories, can be locally generated in a ball contained in them. So they are only non-local in a ring, but they are local if thought inside a ball. This observation, which maybe sounds new, has an immediate and very concrete implication, which is the fact that the description of a conformal field theory in terms of the bootstrap data, so in terms of the spectrum and the three-point couplings, does not need any addition to describe the physics of non-local operators. Of course, the way the bootstrap data will codify the physics of these non-local operators might be very obscure. In some theories, it will be simple. In some theories, it might be very obscure. But in principle, this should be the case. Let me mention that in general, it is complicated. And in fact, in the community, I feel that sometimes they are even thought, these two types of physics, the physics of non-local operators, the physics of Wilson loops and generalized symmetries, are even thought to be completely unrelated from the bootstrap, from the physics of local operators. And this leads to our guiding basic question: what is the imprint of non-local operators in the bootstrap data? So today we are going to solve this question in 2 dimensions. This is probably not the most interesting scenario, but I hope to convey that it is quite fertile and clarifying. So having expressed the main question, let me describe the plan of the talk. The plan of the talk mainly consists also on the takeaway messages of this talk. So in the first part is the core of the talk, where I will describe the equivalence between the broadly known notion of modular invariance in two-dimensional quantum field theory, in two-dimensional conformal field theory, and the notion of completeness, this maybe abstract algebraic notion of completeness that I have just described. This equality will suggest a Finner classification of 2D CFTs, and we will achieve this Finner classification of 2D CFTs for the case of central charge smaller than 1, so for minimal models, and this will be the content of the second part of the talk. And then in turn, this Finner classification of minimal models will provide a unified view, or will streamline the derivation of selection rules for RG flows between 2D CFTs, in this case between minimal models. And this will be the content of the last part of the talk. So let me start by the beginning. So modular invariance, as we all know, is understood as a property of Euclidean conformal field theory on the torus. More precisely, it is the statement that the partition function, as a function of the parameter characterizing the torus, is invariant under the T and S transformations, so these transformations here. But the first question I would like to ask is that what is the local Lorentzian meaning of modular invariance? So what is the real-time meaning of modular invariance, or if you want, in a real-time scenario, how would we verify modular invariance locally? So for example, T invariance is very simple. It implies self-locality of the fields. So the theory would be non-local if T invariance would not hold. The question is, what about S invariance? And what we are going to see is that S invariance is exactly this form of completeness that I have just mentioned, and I'm going to now to show this. There are different ways of seeing this, so we describe those in the article. I'm going to take the simplest path, and the idea is very simple. So we all know that entropies or any entropies agree for commutant algebra, so this is a very basic equation. The question is if this implies that entropies agree for complementary regions, okay? Usually this is taken for granted, but we are going to see that this is not the case. So consider to analyze this question, consider a two-interval region in the circle where our CFT live. This is the red region, so composed of R1 union R2. This two-interval region is characterized in a standard way by a conformal ratio, X. And now, what we know is that the entropy of the red region, the entropy of the additive algebra in the red region, is equal to the entropy of the commutant algebra. But the commutant algebra is not the algebra of the blue region, it's the maximal one. And we conclude that the two entropies will be the same if and only if, in all the states, in all pure states, if and only if the additive algebra is equal to the maximal algebra, and this is the statement of completeness by definition. So the lesson from this is that to track violations of completeness, we can try to track violations of the standard equality between entropies of complementary regions. So a quite convenient quantity to track this violation is the two-interval mutual information. This is defined in this way. The nice thing of this quantity is that it is a difference between entropies, so it is finite because divergences cancel out in the difference. And therefore, it is only a function of the conformal ratio. So we can write it conveniently in this way. So this basically defines the function un of x in terms of the n-Renyi mutual information. Now, I will not go through the proof, but it's simple to see that if the entropies of complementary regions are equal to each other, then this function un of x is crossing symmetric. By this we mean that it is equal, un of x is equal to un of 1 minus x. So summarizing all this slide, to track the violations of this abstract notion of completeness, we just need to track violations of the crossing symmetry property of this function. So let's go for this. Well, in the article we consider all n, but it's very transparent and very simple to consider, very instructive to consider the n equal to 2 case, the second Renyi entropy, which is computed by a manifold of genus 1. Therefore, it can be conformally mapped to a torus and of radius 1 and height L. This was by Matt Hedrick quite a long time ago. And if one follows the transformation, so the crossing symmetry transformation that we talk about that measures completeness, that takes x to 1 minus x, is equivalent to the transformation that takes L to 1 over L. So it is the S transformation of the torus. And most importantly, this crossing asymmetry, we could call it, is equal to the logarithm of the ratio of S-duality transform partition functions. So this equation neatly shows that a violation of completeness, as implied by this quantity being different from 0, entails a violation of S invariance as implied by this right-hand side and vice versa. Okay. So of course, this is now easy to compute, but it is kind of even easier in the limit x goes to 1. The limit x goes to 1 is physically the limit in which the two intervals touch each other. So consider a generic model, a generic 2D CFT, as defined by the spectrum of primaries, basically, by a coupling matrix that tell us how many, what are the combinations of chiral and antichiral that appear in the model. If one uses the modular, the properties under modular transformations of the characters and the definitions of the quantum dimensions in terms of the modular S matrices, after some algebra, one can arrive to our main Warhouse formula, which is this one here. The limit of the crossing asymmetry when x goes to 1 is equal to the logarithm of this ratio of so it is a number. This quantity only depends on the coupling matrix and the quantum dimensions of the model. So it's a very simple thing to compute. And of course, if this number is different from 1, then we have a violation of completeness and a violation of S invariance. So for the part of the audience that is interested in the algebraic perspective of these issues, let me say that this number has an intrinsic meaning. So it determines what is called the Jones index, mu, that measures the relative size between the maximal and additive algebra. So as I mentioned before, completeness, the violation of completeness exactly says that the maximal algebra is strictly bigger than the additive algebra, but there is a notion of relative size. That notion is well defined, is rigorously defined by what is known as the Jones index. And this arrow is quite difficult to show, but one can prove that the Jones index in this case is equal to this number, which is basically the square of this one here. The nice thing of this connection, the connection between this quantity that just depends on the partition function and this Jones index, is that the Jones index is related to the category of superselection sectors of the theory. Again, this relation would take a lot of time to explain, but ask me later if you are interested. So with this, I finish the first part. We have shown that the violation of completeness implies a violation of S invariance, and we have also quantified in terms of this function. So this suggests a finer classification of minimal models. So let me mention the classification of modular invariant minimal models. So two-dimensional conformal field theories with central charge smaller than 1 is known as the ADE classification. This classification concerns both models with both S invariance and T invariance. But we have seen that from a real-time perspective, S invariance is equivalent to completeness, and therefore is not mandatory. Of course, you could put it as an axiom, but it's an additional axiom. In principle, it is not mandatory just if you want a unitary theory in which the OPE works well and the theory is local. So this suggests a thinner classification of minimal models. There is a minimal set of rules to construct those. So we should include the stress tensor net, so the identity sector. We should impose locality, which includes T invariance, because T invariance is self-locality of the fields, but this is a little bit more, because it also implies that the operator product expansion will produce only fields that are local, also, that are self-local. So the closure of the operator algebra should be such that, that the algebra is closed on self-local fields, so that the theory is local. So one could think that by imposing these conditions, one is going to get necessarily S invariance, but we are going to see that this is not the case. Actually, there are plenty of models that satisfy these axioms, and they don't satisfy S invariance. So let's start by the simplest one, which is the case of C equal to 1/2. So here we see the known modular invariant free fermion and Ising model, but we also see 4 incomplete models. In the bottom part, we see the identity sector. This has the largest violation of completeness, is the one that is farther from the top. And then we have 3 models in the middle. Climbing up this tree, the Jones index decreases. For example, here we have a model which is well-defined, which is just the identity plus the epsilon. Or here we have the models that are well-defined, which are just the identity plus a chiral fermion. For this talk, I won't have time to explain all the classification, but let me just explain the submodels of the diagonal series for a general central charge. So the central charge in minimal models is labeled by an integer number, m. And defining this function here, for odd m, we have this kind of hexagon. So let me explain it a bit. So again, at the bottom, we have the chiral algebra. This has, again, the largest violation of S invariance, or the largest violation of completeness. We can go to the first node by adding fields with S equal to 1 and R odd. These R and S are the usual parameters that label chiral representations in minimal models. This one can compute using the formula, the previous formula, that the Jones index is given by this function here. And one can guess a category of superselection sectors that will match that index. And this would be the affine Lie algebra SU2 at level n-1. And one can verify by direct classification, by direct computation, that the fields of the theory, the fields that are lack in this node, actually they can be divided into categorical multiplets furnished in the fusion rules of this category. We can add the next node appears when we add all R. Again, the Jones index decreases a bit. And in this case, the category of superselection sectors decreases a bit. It's just the even part of this affine category. We can add, the next step appears when we add all R and all S that are odd. And the index is now very small. And it is consistent with a group, which in this case is the abelian C2. And then we can add all diagonal fields. We arrive to the modular invariant completion. We could have gone in other directions. All these nodes are very similar to these ones. They just change a bit the Jones index and the categories of superselection sectors. So in the article, we discuss the submodels of the diagonal series and also of the non-diagonal series. Here is an example of the case n equal to 11 that contains like the three A, D, E modular invariant completions and all submodels. We see that there are submodels that are particular from non-diagonal and that can only be completed with a non-diagonal, this one and this one. And well, we have all, again, by the formula that I mentioned before, one can guess the categories of superselection sectors that each node in the tree has. Okay, so this classification, let me say that this classification is consistent, and indeed it can be considered as a re-derivation of the classification of possible superselection sector categories found by Yasuyuki and Roberto back in 2005. But I want to stress the differences. So first, I want to remark that we have classified field theories. So we have classified specific local models with the spectrum of primaries in each model, while they classify only the allowed pattern of symmetries. In particular, you could have two models, two quantum field theories with the same symmetry pattern. Also, another difference is that they use algebraic techniques, while we have just used a standard OPE. Well, I didn't mention, sorry, to build all these trees. What one has to do is to, I don't know, take the chiral algebra, put some primary, and then close the algebra, and do that with all the primaries and all possibilities. So we only use the OPEs and the formula that I mentioned before. So this gives a lot of support for the algebraic techniques. It's a very non-trivial check that we have re-derived their classification. But it is true that both classifications are almost the same. And this means that symmetries almost determine minimal models. So conformal field theories for central charge is smaller than 1. So I want to finish with the last part in which we see the implications of this structure into the derivation of selection rules for RG flows. So the starting observation is very simple. So if the flow, we have a flow between minimal models. If the flow is triggered by certain field phi, then we can think the theory where the flow is happening as the one with the stress tensor T plus phi. So this defines a local model. We could call it the neutral theory. We call it the neutral theory because it's the invariant theory under the remaining generalized symmetry that survive the perturbation. Okay? So we have this model. It's just the stress tensor plus the perturbation. But this model is not necessarily modular invariant, and it typically is not going to be modular invariant. And all the selection rules basically come from the fact that the whole algebraic structure above the node acts as a witness, so it doesn't change with the flow. More precisely, if the flow is not massive, like all global and relative Jones indices above the perturbed node are preserved. Equivalently, the structure of possible completions above the perturbed node is preserved, and maybe in a more unified manner, the category of superselection sectors of the perturbed node is preserved. Okay, so let's see an example. So, well, the nice thing of this classification is that we can check diagonal and non-diagonal in a unified manner. But let's just consider the example that was the seminal example that was studied by Samologikov back in the 90s. So Samologikov perturbed the minimal model with the perturbation 1, 3. And now if we construct this theory, the theory of the stress tensor plus the perturbation 1, 3, for this is this node here, okay? And then the selection rules tells us that we should look for theories with central charge smaller that have the same pattern, all the same structure above the node. And there is only one. For m equal to m minus 1, we have this node and has exactly the same Jones index and the same structure of completions and the same, all the same different Jones indexes. Let me also say, just to finish, that we can also get a match between operators in the UV and in the IR by classifying the fields into categorical multiplets of these superselection sector categories. This is done in the article. Please ask me later if you are interested. So with this, I finish. Just to finish, let me come back to the motivating question. So the question maybe was abstract at the time. So the question was, what is the imprint of non-local operators in the bootstrap data? Or say it in another way, how the bootstrap data codify the physics of non-local operators? We have solved this question in 2 dimensions. Let me mention that, let me stress that all these superselection sector categories, all these physics, were just derived by the bootstrap data via the workhorse formula that I explained before. So in this case, all symmetries, all possible symmetries and all possible superselection sector categories, well, were just derived by this bootstrap data. More generally, maybe in this audience it's not important to stress the importance of symmetries in quantum field theory and in string theory, but let me stress that the key role and subtle role that local physics play in this regard. All the symmetries one should be able to determine them from local physics. And just to finish, for the future, of course, the most interesting case is to understand how confinement is codified in the bootstrap, and well, hope that I can bring good news in the future. Thank you very much. Yes.
Thanks for the talk. I have a question. So in the morning, we heard a beautiful talk about pure Chern-Simons theory, now in 3 dimensions. Now, pure Chern-Simons theory doesn't have any non-trivial gauge invariant local operators. So pretty much all the non-trivial information is encoded in the Wilson lines. So I'm just curious, how does your formalism would distinguish different kinds of pure Chern-Simons theory? No.
This is I'm talking about symmetries that would appear in local field theory. Yeah, it wouldn't apply to that. These don't cover those. One interesting question is, what is the space of topological field theories that arises as limits, as infrared limits of a local field theory? And in that case, I mean, for that space of theories, which I don't know if it's the whole space of topological field theories, for that space of theories, those Wilson loops and that symmetry category would be basically the category that survives, well, the massive flow.
Okay, thanks.
Other questions? Sorry, no.
Well, I don't see why it would not apply for the Chern-Simons case.
No, it applies.
So the first discussion of the rings and so on, wouldn't that apply also to the Chern-Simons case?
Well, the thing is that in principle, I mean, the first discussion. So for us, it's very important that
some of the algebras might be trivial, but
all the local algebras are trivial. What in principle also the shrinkable loops. So for us, there is a huge difference between loops that are shrinkable in space and loops that wrap a non-trivial. So the ones that we are interested in are the loops that can be shrink to a point. Those have non-trivial physics in a local field theory, while in a topological field theory, probably they are trivial. The expectation value is just 1.
Right, but in this particular case, for example, if I understand correctly, the algebra AR would be trivial, and the A max will contain the Wilson loop.
Yes, correct. But the expectation value would be, yeah, correct, yeah. But so that's what I'm saying. Okay. The question is whether that theory you can arrive at it from an RG flow, from a massive RG flow in which that Wilson loop can be generated by a local operator, by local operations. Yeah, I mean, if you want, you can extend it in that way. I agree with you.
I mean, I think I was also going to ask some version of the same question, but to pick a concrete example, let's talk about the pure Z2 gauge theory in 1+1 dimensions.
Yes.
So that theory is not complete in your sense?
Depends on what, probably there will be some.
So this theory has a local operator and it has a Wilson loop, and that's it. But you can't build the Wilson loop, the holonomy going around the circle out of the local operator. But I think the partition function is modular. Seems fine to me.
Yes, there's no problem. I'm not talking about that kind of theory.
But I thought you said that completeness is necessary to have it be modular. Did you not say that?
For a local theory.
But this is a perfectly local theory. It's
No, in which operators are generated locally.
I thought you were trying to say that if you have a theory that's not complete, that it won't obey modularity. Are you not saying that? Maybe I reversed the logical implication. So the theory I said is it's local in the usual sense, but it's not complete.
It's not local. I mean, it's not local in the sense that operators cannot be locally generated.
Yeah, that's why I brought it up. But
the
partition function is fine.
It is. I don't have a problem with that theory.
Okay, all right. But what's a theory you do have a problem with?
No, I don't have a problem with any theory. I'm just describing features about some theories. So there are some quantum field theories. These results apply to a zoo of quantum field theories.
I mean, are there theories that aren't modular?
Continue that.
Yes. Thank you.
Let's thank Javier again. Okay, good. So our next speaker is Janet Hung, and she'll be, take it away.
So I would like to thank the organizers for giving me an opportunity to speak here, and apology if you have heard versions of this talk. And I would also like to thank my collaborators for developing this program together, and particularly I would like to thank Yikun Jiang, Lin Chen, Bingxin Lao, Gong Cheng, and Zheng Chenggu for their crucial inputs in this program. So what I'm going to talk about today is a way to construct very precise holographic tensor networks directly from the CFT. But before that, maybe I should motivate a little why we still care about tensor networks. I think it is realized from very early on that it is the most natural framework that convert quantum entanglement into geometry, and therefore naturally provides an arena to realize the Ryu-Takenagi formula. Moreover, it is very natural to construct local map between CFT and ADS degrees of freedoms through this tensor network. And so it might produce a microscopic understanding of the ADS-CFT correspondence. Since then, there has been lots of important works trying to constrain and construct models of tensor networks that reproduce different facets of the ADS-CFT dictionary. But there remains some important question. For example, how do we see what is the CFT this tensor network is describing? And if the holographic duo contains gravity, how do we see the Einstein-Hilbert action? To make these questions more precise, let's just put down a wish list for tensor networks, holographic tensor networks. So first of all, we certainly do want to have control of the CFT. We want to have exact data of the kinematics and the dynamics of the CFT. Secondly, if this tensor network is discrete, then we certainly want it to be graph independent. Moreover, we also don't want the tensor network to be fixated to describing one semi-classical geometry. We hope that it would be more background independent. Third, from the CFD data, we hope that there would be an emergent Einstein-Hilbert action that can be described in very precise terms. And better still, if there is a UV-complete quantum measure that tells us what geometries that we should sum over. Then there is this radial direction in the ADS space that corresponds to RG flows in the dual theory. And we certainly hope to see that in this holographic tensor network. And ultimately, if we can realize all of the above, then that should give us a non-perturbative boundary to bulk map. So in the rest of this talk, I'm going to present a brand new strategy that we developed to constructing a network as such. So in this tensor network, we're going to directly look into a space-time tensor network rather than focusing on tensor network that describe wave functions so that covariance is automatic. And in this strategy that only works at present only for ADS3, CFT2, and not all I'm not claiming that all models can be constructed in this way, but I don't know what are the boundaries of where it works. Nonetheless, let me describe the idea of this strategy. First of all, we need a new way of triangulating 2D CFT. But this is not a naive discretization. It is a very special discretization that makes use of boundary CFT 3-point correlation functions and something called shrinkable boundaries. Using this method, we're going to produce exact tensor network for 2D field theories. Then, from this discretization, it would miraculously produce for you a 3D path integral from these BCFT OP coefficients. Therefore, we would read off from this discretization an exact holographic tensor network. And this 3D bulk is actually, what it does is to make the 2D global generalized symmetries, including non-invertible symmetries, manifest. And you can check the large C classical limit of this bulk that emerges. And when this bulk preserves very thorough topological lines, you can show that a precise Einstein-Hilbert action would emerge. And we can also consider renormalization group flow in the field theory, and we can show that it corresponds to radial evolution in the bulk geometry. So this is the overview of my talk. I would describe our strategy in 4 steps, and then I would conclude with some summary and outlook. So step 1, as I described, we need to discretize this path integral into pieces. And the way we do it is by cutting and gluing. Cutting and gluing is not new in 2D CFT. We decompose path integrals into pairs of pans and cylinders. But here, we're going to cut the CFT path integral into triangles. These triangles have 6 labels. The corners are actually small segments of conformal boundaries. They're labeled by the conformal boundary of the CFT. And the edges are labeled by primary and descendant labels corresponding to boundary changing operators that live between these boundaries sigma 1 and sigma 2. Each of these triangles can be computed by looking into a conformal map that maps it to a 3-point function in the upper half plane for these boundary changing operators. And this conformal map controls for you the precise shape and size of these triangles. Okay, these things can be computed, and you can look into our paper how it is computed. So once you have got these triangles, you can go back and try to tile the surface that on which you want to compute the 2D CFT path integral. And the gluing rules for this triangle is simple. Every 2 triangles that share one edge, you just sum over all the primaries and descendants on this edge. So once you have done that, the path integral is almost what you want, but not quite. Because remember, every single corner is a small segment of conformal boundary. So when you have several triangles sharing one corner, it would leave behind a small hole that is labeled by the conformal boundary condition at this vertex. So the next step is to shrink this boundary so that we recover a smooth path integral. And to shrink these holes, we need to introduce something called the shrinkable boundary condition. And this shrinkable boundary condition, the idea of which is that if you have some fixed conformal boundary, it would actually break the topological symmetries of the CFD. So what you want to do is to construct a weighted sum of these boundaries so that topological lines can pass through these holes as if they don't exist. Then you can protect the theory so that it flows back to the original CFT in the infrared limit. And putting it in a different way, if you look at these holes from the closed CFT channel, they are described by Carty states, and you can design weighted sum of these Carty states so that it is rotated to the vacuum Ishibashi state. And these weights can be computed readily in a rational theory, and these weights are precisely those that satisfy this symmetry condition. And these are the so-called shrinkable boundary that we are putting in. So summarizing, the smooth CFT path integral can be written as a product of these triangles product together, and then we sum over all the primaries and descendants at each edge, and then we finally sum over all the conformal boundary conditions weighted by these weights at every corner. And finally, we take the limit that this whole size goes to 0, and we should reproduce the smooth CFT path integral. So let us note here that this is a tensor network representation of a CFT path integral, where you can treat each of these triangles as a 9-labeled tensor, and the bond dimension of these tensors is infinite because the number of descendants is infinite. And this is what you expect when you want to reproduce a continuous field theory from a discrete type in a discrete way. But this is not only a tensor network that represents the CFT, it's also a very efficient way of representing the CFT. So in any actual computation, in any realistic computation, when you sum over the edge states, on the triangles, you have to do a truncation. So let's suppose you truncate only up to a few descendants in every family. And we show that even if you truncate it to only a few descendants kept in each family, you can still recover the path integral to very high accuracy. We benchmark our result against the state-of-the-art tensor network numerical results, and we find that our accuracy when bond dimensions are comparable is comparable to the best tensor network results. So this also resolves a rather long-standing question: what exactly is the CFT explanation of these numerical results, of these numerical algorithms that recover, for this tensor network that recovers fairly efficiently the CFT data. So this basically provides an explanation. Okay, so what we have up to now is a precise recovery of CFT from a tensor network that can be computed analytically. And this is a graph-independent tensor network because the triangulation of the path integral is arbitrary. You can change the triangulation any way you wish, and it will still recover the same CFT path integral. All you're changing is the shape and size of the triangles. And so this is where we are. Okay, so second step is to read off a 3-dimensional bulk from this triangulation. As we described, the 2D CFT path integral is now written in terms of these triangles. And R is denoting the radius of the small hole that we have to take to 0 eventually. But now each of these triangles is a 3-point function, as we described in the previous slides. And the 3-point function can be separated into the structure coefficients and the kinematic part, the conformal block, the 3-point block. Now, let us collect all the structure coefficients and also the weights that depends on the conformal boundary conditions and sum over the dummies corresponding to the conformal boundary conditions. And this object here turns out to correspond to something that is very well known in the literature. It is actually a 3-dimensional topological field theory path integral called the Turaya-Viro TQFT. So how do we see the third dimension emerging? Just stare at these structure coefficients. They are related. They're known to relate to these so-called quantum 6J symbols. And this has a geometrical meaning of, they can be interpreted as a tetrahedron in 3 dimensions. The 6 edges of a tetrahedron corresponds to the 6 labels on the structure coefficient. And if you stare at this expression, you realize that it is filling up a 3-dimensional space such that the boundary of this 3-dimensional space is the original 2D CFT, the original surface on which the 2D CFT resides. And so this is a cross-section of this 3-dimensional space. The BCFT structure coefficients basically fills up a 3D space. And the red edges corresponds to the primaries that lives on the surface of the triangles on the CFT, and the black edges of this tetrahedron corresponds to the conformal boundary condition at each corner. This weighted sum here coincides exactly with the formulation in Turaya-Viro about how to do the quantum measure of the sum in the interior of the path integral. Let us also note that you can also interpret these weighted sum as encoding a topological boundary at the interior of this solid. But nonetheless, the important take-home message is that this is a path integral over the yellow region that produces a wave function that lives on the surface of the red surface, which the CFT lives. Now, what about the conformal blocks? Let's collect the conformal blocks together and sum over the dummies, which is now the descendant labels. This produces for you another wave function that depends on the surface red edges, and the final wave function, the final path integral, is basically the overlap of this topological wave function and omega. And so now we see a three-dimensional path integral emerging, and let us note that this three-dimensional path integral is triangulation independent, even though you started with a very specific triangulation specified by the CFT, but because it is a topological field theory, you can actually change the triangulation, and this would become important later. And so this three-dimensional bulk is really a gauge theory of the generalized symmetries in the CFT. And the modular invariance of the CFT is encoded in the boundary conditions, in the conformal boundary conditions that is in turn encoded in these measures that tells you how to sum over the edges. And that specifies for us a 3D bulk state. This is, in fact, an explicit realization of the sandwich construction that John has reviewed for us yesterday. And the topological boundary specified by the conformal boundary conditions is this other side. The omega forms this part of the boundary condition. It's a sandwich that realizes 2D CFT. And what is special here is that when the bulk is capturing a maximal amount of the symmetries of the CFT, the bulk actually captures CFT dynamics. It controls the structure coefficients of the CFT. So what we have up till now is that we have obtained a 3D graph-independent path integral, and it encodes modular invariance of the 2D CFT in the measure or in the topological boundary, and the global symmetries of the CFT are showing up as gauge symmetries in the bulk. Then the next step is that we want to see gravity. So far, there is no gravity. It's just a 3D path integral. To see gravity, we need a large C CFT. And the candidate that we're going to take is a simple theory, namely the Liouville theory, which has a large central charge limit. So we're going to now redo the strategy that we have been doing previously to have a Liouville CFT path integral on 2D and then cut it into triangles and see if we can read off a three-dimensional path integral. So fortunately, the conformal boundary conditions of the Liouville theory, that is a close collection of them that has been worked out, the FZZT states. They are labeled by a positive real number P sigma. The boundary changing operators is also labeled by a positive real number, and the structure coefficients, the 3-point structure coefficients of these boundary changing operators have also been worked out in the literature. And it can be massaged into this form and this part is again a quantum 6J symbol of the quantum group UQSL2R, which we note is also the crossing kernel of Virasoro conformal blocks. Now the next ingredient we need is how to close the holes. And we figured that one can pick the so-called plantural measure for each corner variable, and it also corresponds to the Carty density of states, and this would do the trick. So now we can write down the Liouville CFT path integral as triangles, and we collect all the structure coefficients together. We have to sum over all the corner variables weighted by this plantural measure, and then on the other side we have the conformal blocks. And we would expect that this part should reproduce a 3D path integral that perhaps is related to Einstein theory. But how to see that? So in order to see Einstein actions, to see geometry emerging, you need to take the large central charge limit. And the large central charge limit corresponds to taking this parameter b to 0. And at the same time, we rescale the p variables to be L over 2 pi b, keeping L finite as we take b to 0. And in this case, this 6J symbol has a limit which is given by the exponential of a volume of a hyperbolic tetrahedron, and plus another term that depends on the dihedral angle at edge I, spanned by two phases that meet on this edge. So this volume is a function of these L's. And now these L's, which came from the P's, are now geodesic lengths of the hyperbolic tetrahedron from each of these 6J symbols. So, and now you can also use the relationship between the central charge and the gravitational constant C equals 3L over 2Gn and convert this B into the gravitational constant. What you find is that this term coincides precisely with the on-shell Einstein-Hilbert action with a negative cosmological constant, and this term, the coefficient, coincides exactly with the Gibbons-Hawking term or the Hayward term that is there when you have conical singularities that is around a particular edge that is shared by several tetrahedra. So summarizing, what do we have? We have the Liouville path integral is now written as the psi. Psi is now a bunch of hyperbolic tetrahedra put together, and then it has boundary conditions given by these conformal blocks, and we're now summing over all the alphas. We're integrating all the alphas with a very precise quantum measure, and that corresponds to summing over all different lengths for the geodesics for the tetrahedra. So that gives you a precise sum over geometries of different sizes and shapes of this tetrahedra that make up the global shape. And this sum would reproduce by construction the Liouville CFT path integral. Let us note that at general C, the path this part of psi is actually the Virasoro TQFT folded. This planetary measure that we have chosen, again, encodes a topological boundary, and it corresponds precisely to the fold when you fold the Virasoro TQFT. Okay, so up to this point, what we have is that Einstein-Hilbert action in the semi-classical limit is recovered. A non-perturbative quantum measure for this sum over geometries is read off from the CFD, and we find a non-perturbative map between local CFD degrees of freedom and bulk geodesics. The P variables become geodesic length of the dual theory. So let us note that this bulk is basically a bulk that is determined by preserving of topological Virasoro lines. And Liouville theory is only one example which preserves this symmetry. And therefore, we believe that this story should be somewhat more general than describing the Liouville theory alone, even though we don't have a general solution of all the structure coefficients for more general irrational CFD as of now. So finally, let me also talk about RG flows and how do we see a bulk radial direction emerging from this picture. So as we have described, the path integral of the CFT is now written as the overlap of a three-dimensional topological wave function with some appropriate boundary conditions. So what is the Wheeler-DeWitt equation? It now becomes the Hamiltonian constraint that you act that is satisfied by the topological wave function. And now we also need an RG scale, and there's a natural candidate. We pick the triangulation of the 2D surface, so the lattice scale plays the role of a natural RG scale in the 2D theory that we denote by lambda. So now, in order to see RG scale, we need to change. It means that we need to change the triangulation systematically. And to change the triangulation, it is guaranteed by the Hamiltonian constraint satisfied by the wave function. So this is again the cross-section view of the 3D path integral, and consider that this is the original triangulation selected by the CFD, but suppose I want to change this, this part of the triangulation and cross it into this form. This is allowed by the Hamiltonian constraint, and now I can interpret this top triangle as a map of two surface edges to one edge in the interior. So you can now interpret this triangle as an RG operator that is completely dictated by the symmetries. And it is, and since this triangle is also a quantum 6J symbol, so this, if I do this retriangulation globally, mapping surface, coarse graining surface edges into fewer number of edges in the interior, this gives me a 3D path integral between essentially two radial slices. So for more details, see Jiang Yuquan's poster outside. But then let me add a few more words. So, so if I do the coarse graining globally, I collect a bunch of triangles, and I can recursively do this retriangulation in the bulk, and it would produce a tensor network that goes into the bulk of the ADS space, and it would look exactly like a mirror tensor network if you draw these tetrahedra out. And now, how do I derive the Kalin-Zemanzik equation from this knowledge? What you do is that the wave function, by retriangulating, it spits out these triangles, which we call the RG operator. And now you can absorb this RG operator by the boundary condition. At the CFT fixed point, the boundary condition is also an eigenstate of this operator. But if you deform the CFT away from the fixed point, then this omega, this boundary condition, would flow when you absorb this RG operator to omega. And by studying this flow, you would recover the Kalin-Zemanzik equation. So let us summarize the slogan here. By considering symmetry-preserving RG flows, it would correspond to a path integral of geometries between two radial slices if the symmetry concern is topological versor lines. So let me be a bit more explicit. You can, in fact, consider very specific RG flows perturbed, driven by TT-bar deformation. The way to do that is that, remember, we have a host in the triangulation. If you don't take R to 0, but rather keep a finite but small value of R, then from the closed CFT channel, you realize that each of these states, each of these Ishibashi state is given by the vacuum state plus the next term for finite R would be basically a TT-bar operator insertion. So just by keeping a small but finite value of this radius, it corresponds to deforming the CFT by TT-bar insertion. And now if you absorb the boundary, if you absorb these boundary conditions, you take the RG operator and get it absorbed in the boundaries, you'll find that all it does is to change the whole size of the host. When you merge several triangles into fewer number of triangles, the ratio between the host size and the edge length changes. And so by studying this flow under this under this merging of triangles, we can reproduce the Kalin-Zemanzik equation that exactly agrees with the field theoretical analysis. And so here, summarizing, we can reproduce RG flow in our construction. And let us also note that we have actually already made use of crossing symmetry when we constructed this RG operator. So let me conclude. So I hope I have convinced you that at least within the framework, we are able to construct tensor networks that meets most of the stuff we presented in our wish list. And moreover, because we are constructing path integral, we can easily convert that path integral into constructing wave functions. And so you can construct wave function by looking at path integral on a disk and compute entanglement entropy. There you would see that this very famous happy perfect tensors would emerge in a slightly deformed way such that the entanglement spectrum is exactly correct, but these structures actually would be captured by an exact tensor network. And so the final message is that it seems that this is a constructive approach to deriving non-perturbative equivalence between CFT and some kind of holographic duo, may or may not be gravitational. And one last conclusion is that when you capture the maximal set of generalized symmetries, it seems that it would be able to constrain the dynamics sufficiently, at least in low dimensions, to reconstruct the bulk precisely. And we believe that this might be a more general feature even in high dimensions. And also note that we did not really sum over all possible geometries in the three-dimensional bulk. The sum of the geometry is tailored for each of the CFT. The measure is determined by the topology topological boundary condition, but it is tailored for each modular invariant CFT. And so for different CFT, we might have to sum over something different. And if we sum over some other things, it might also lead to ensemble averages. And this has some implication to the factorization puzzle. If you have two CFTs that are not connected, you can always think of this as a bulk with a topological boundary. And again, topological boundary in this framework can be naturally expressed in terms of a quantum measure, or sum over geometries. And so it would allow one to figure out a sum over geometries that factorize the geometries. So this is the final slide. There is a bunch of things that we still hope to do. And generalizing to other dimensions, looking for black holes. And so let me just end here. Thank you very much.
Thank you for a very nice talk. But there's something I didn't understand. Maybe I missed it. I think the key structural property of the bulk that leads to holography is the fact that the Hamiltonian is a boundary term. It follows from the Wheeler-DeWitt equation, but it's only one component. It's the integrated Wheeler-DeWitt equation, which tells you the ADM Hamiltonian can measure the energy in the bulk. I didn't see how you could see that structural aspect from this analysis. Is that something that one can clearly see from this analysis? That the
You mean the integrated form of?
That's right, that's right. The bulk energy is measured by the metric on the boundary. That's somehow the most important part of the bulk for holography. I mean, can we see that easily from this analysis?
To be fair, I have to think about that. I don't have an answer on top of my head. Sorry.
Okay, thank you.
The reason being that I don't have a convenient metric to use, and all I have at my disposal are geodesic lengths, and so I'm a bit confused about how should I read that off. Yes.
Okay, thank you.
Other questions?
Could you say again for which CFTs this construction works? Did you use that they were minimal models or?
They're not necessarily minimal. So for the case of rational CFTs, then this is so where I have used the fact that it is a rational CFT. Sorry. It's at this point. Sorry. No. Is here. The fact that I know that these 6J symbols corresponds to, I know that these structure coefficients correspond to 6J symbols. I made use of these series of works in the early 2000s that that try to a constructive approach to solving structure coefficients of rational CFTs using tensor categories. And so in general, for irrational CFT, I wouldn't be able to say the same. But then if for explicit examples such as the Louville, it seems to adopt that structure. One extra and also these weights depended, I could solve for these weights readily in a rational CFT, but I would not be so certain in a generic theory. But one extra comment that I have is that if the theory can be decomposed into Virasoro representations, then this URG, this RG operator would still be the same because it is only making use of the crossing kernels of Virasoro representations. But the structure coefficients itself, which is the UV completion that tells you how to close this 3D geometry, would not be readily available if I don't have, for a generic irrational theory.
Let's thank Janet again. And before we go, there'll be a quick announcement.
Yeah, so now we have a long break, 1 hour or a little less until 4:30. This is for coffee and posters, so please go see the posters that are here or across the hall. Poster owners run now, and you have to be there.